Yeah, so I feel very honored to speak at a conference, at a birthday conference for Tate. I mean, I did my undergraduate thesis under him on an explicit spherical spherical completion of QP bar, and I also did my PhD thesis under Ken Ribbett. So I guess Tate is both my mathematical father and my mathematical grandfather. So, okay, so yeah, so I'm going to talk about the origins of the Tate conjecture. So most of my talk is going to be about things from way back, the history, and then this is really the first part of a two-part talk, and Yves-André will speak about the more modern and motivic point of view of things. All right, so as Jim Milne explained yesterday, that the Tate conjecture came from Tate, from work that Tate was doing with Artin, trying to understand what the Bernstein-Swinnerton-Dyer conjecture and the fineness of the Tate-Shafer-Average group would say in the function field case. What would they say if you translated it into statements about the total space of the family? So okay, so let me get started. So okay, so first of all, okay, so yeah, but there will be some overlap with Milne's talk yesterday. So I'll go quite quickly through this. Okay, so I think you all know that for a global field and an abelian variety, you can define the Tate-Shafer-Average group as the kernel of this map of H1s from the global H1 to the product of the local H1s. And it's a conjecture that this group is always finite. And I've heard that it's not clear who made this conjecture. Apparently, Shafer-Average in 1962 said that he had serious doubts about this statement, and Tate said that he wasn't the one who came up with this conjecture. So I don't know. Okay, so whatever. Anyway, so maybe Shafer-Average came up with it, but he didn't believe it, and then okay. Anyway. So yeah, and this has been proved in some cases. So right now, for example, for all elliptic curves, now that we know the elliptic curves are modular, all elliptic curves of analytic rank less than or equal to 1. Yeah, and Tate said in 1994 that part of the reason he made part of the reason he believed this conjecture is because otherwise Galois cohomology would be a mess, and I guess Tate doesn't like having a mess. So, all right. Okay, so to translate this now, to get to the Tate conjecture, I want to explain. Be in the setting that Milne was discussing yesterday for a fibered surface. So B is going to be a curve over a finite field, and so its function field K is a global function field, and then you can either start with a curve above K, or you can start you can spread out to a surface, or you can start with a surface. So X will be a surface, and then over this curve. And yeah, I'll assume that everything is smooth, projective, and geometrically integral. And so I'll just call that nice from now on. And I'll also assume that the generic fiber is also nice. And J will be the Jacobian of that curve. And you can also define the Brauer group as the second atoll cohomology of X. So this is all right. And then a theorem that Artin worked out in some cases, and then Milne in general. Actually, I'm stating only a partial. What Milne proved is actually stronger than this. He also considered the number field setting. But anyway, so the theorem is that you can translate the fineness of Sha for this abelian variety over this global function field into a statement about the surface, and so it's that the Brauer group should be finite. And so if you believe that Sha is always finite, then you should also believe that the Brauer group is also finite for every surface over a finite field. And well, okay, this is sort of tangential to this talk, but Artin also asks whether it's finite even for every scheme that's proper over spec Z. So okay, anyway. All right, so the third step in getting to the Tate conjecture is now to translate this fineness of Brauer group into some statement about cycle classes. So okay, so here, so X is going to be a nice variety, and we'll write X bar for the space change to the algebraic closure, and G will be the absolute Galois group. So if you take Tate cohomology of this Kummer sequence, which you can think of as being sort of this is sort of a replacement for the exponential sequence in complex analysis that you use to prove the Lefschetz 1-1 theorem. And so if you do the analogous thing here, where you take this and you take cohomology, and so H1 of GM is pick, and H2 of GM is Brauer group, and so you get pick going to pick, and if you cut off the long exact sequence on that side, and you cut it off on the other side also from using the Brauer group, kernel of the Brauer group to itself, then you get this short exact sequence. And if you do the same thing, not just for L, but for L to the n, for all powers of that prime, and then take the inverse limit, then you get this sequence here. Oh, sorry, I think I should have put. Yeah, okay, sorry, I should have put a quotient up by the pick. Oh no, it's okay. Never mind. Pick 0 is one of the nice things about finite fields is that pick 0 is always a finite group because it's the points of an abelian variety over a finite field. So yeah, so I don't have to worry about the difference between pick and narrow severity. Okay, so this is so you get this short exact sequence. And this thing here, just because this would be true for any group. If you take this kind of inverse limit, you always get something torsion free. Okay, so now if you believe, if you're conjecturing that this Brauer group is finite, that'll mean that this inverse limit is 0, because eventually, because the maps in this inverse system are multiplication by L, so it can't go on. You can't keep dividing by L if Brauer group is finite. So Arden and Tate proved these theorems that this finiteness is equivalent to this inverse limit being 0. But now you see that that's the same as saying that this map should be surjective. It's automatically injective, but the conjecture should be that should be surjective now. And you can also restate this in terms of, you can tensor with QL. Obviously 3 implies 4 here, but you could also go the other way, and that's because of this torsion freeness here. So, okay. And the other thing you could do, this is kind of a weird Tate cohomology, because usually when you take Tate cohomology, you do it for a variety over a separably closed field. You want to have something geometric. But this is for the arithmetic variety itself over FQ, but you can replace that. You can understand that Tate cohomology with QL coefficients as the Galois invariance of the same thing for X bar. There's a little argument you need for that. Use the Hochschild-Serre spectral sequence, and you also need to know. It turns out to do the calculation, you need with the spectral sequence. You need to know that the eigenvalues here are not 1, but that's true for just because of the weight. It comes from the Weil conjectures. So, and for H1, the Weil conjectures were known back then. So okay, Right. So now we have this conjecture. So now, because of this, you should believe. If you believe in finiteness of Sha, then this map from here to here should be surjective. And this is the sort of the first interesting case of the Tate conjecture. Okay. Oh, and you can also replace the Picard group by divisor group if you want to. It doesn't matter because you can divisors surject onto the Picard groups. It's the same thing. Okay, I just want to do this because I'm going to just because the way I'm going to state the conjecture, the generalization on the next slide. Okay, right. So now here's finally is the Tate conjecture. So this was made in Tate's 1962 ICM talk for divisors on a surface over FQ, and then in full generality a few years later, or at least that's when it was published. Okay, so first of all, he generalized it to the case where instead of a finite ground field, you have an arbitrary finitely generated field. So that's a function field of a variety over FQ or of a function field over Q. So it can have an arbitrary transcendence degree over the prime field. And then you have the separable closure and the absolute Galois group, and you start with the variety now over this field, and you have its space change to the separable closure. and then you can talk about, I mean, instead of divisors, you talk about cycles of arbitrary codimension. So you fix a non-negative integer r, and you look at codimension r closed integral subvarieties, and you take the free abelian group on those. So those are the algebraic r cycles, and yeah. So then, okay. So r equal 1 gives you the divisor group, and then the conjecture is that if you look at the cycle class map, so this is the one that generalizes the map from pic tensor QL to H2 Galois invariants, then that map should also be surjective. So if you map, so yeah, so these cycles are these are the cycles that are defined over K. So their cohomology classes are going to be automatically Galois invariant. Oh, by the way, I guess I never explained this parentheses R. If I go back to the previous slide, so here, this ZL1 by definition was the inverse limit of mu L. So it's a group that's, it's a sheaf actually, but anyway, it's isomorphic to ZL except the Galois action is different. And so the Galois action is given by the Galois action roots of unity. And then if you have ZL twisted by 2, that just means this thing tensor square. And so on. And you can define it, yeah. So, okay, so that tells you what this is. And you need to do that because that's where the cycle class map naturally maps to, just as the Picard group naturally maps to H2 with twisted by 1. Okay, so yeah, so this map, which is automatically injective, this map, oh sorry, not the way I stated it. Never mind. Okay, but anyway, the conjecture is that this thing should be surjective. So onto these Galois invariant classes, and the Galois invariant classes are also called Tate classes. All right, so that's the conjecture, and so it'll be called T sub r in the rest of this talk. Tate also called it T sub r in a later time. Tate said that T stands for Tate. So okay, and you can compare this to the Hodge conjecture. So the Hodge conjecture is a similar statement for a variety over complex numbers, and it also tells you something about the image of algebraic cycles in cohomology. Except there you take the Betti cohomology or singular cohomology with Q coefficients, and you intersect this with the RR part in the Hodge decomposition of the complex cohomology. And then again, the conjecture is that the classes here that come from algebraic cycles are the ones that are in this RR part. Yeah, both these conjectures are important because they give. Well, one way to say what they're doing is they're giving you ways. If you believe them, they're telling you that how to construct, or they're telling you things about the existence of R cycles in cases where you don't necessarily have a nice way to construct them. It gives you a way to prove their existence in terms of linear algebra stuff, in terms of cohomology. And so they're both conjectures of that type. So that's why they seem to be so hard, because how you have to prove something like this, you have to actually cook up some algebraic subvarieties, and yeah. Okay, and people have tried to make integral versions of this. So for the Hodge conjecture, you can try to not tensor with Q and just use Z here and maybe mod torsion maybe. And you can similarly here, you could try to do this with ZL instead of QL, and that actually worked in the previous case. This thing worked here for ZL, but well, assuming finiteness of Brauer group or finiteness of Sha, but it's now known that both of these are the integral. Pretty much most of the integral versions any you think of seems to be false in higher codimension at least. So a bunch of people. I'm probably missing some names here, so apologies to other people in the audience who've proved things here. Yeah. Okay, so this is the main conjecture, this T sub r. I want to explain some other related conjectures that are sometimes also considered to be part of the Tate conjecture. So in order to do these, I want to talk about various equivalence relations you have on cycles. So, Okay, so there's some subgroups you can define in this thing, which is the group of R cycles, the free abelian group on the codimension R subvarieties. So rationally equivalent to 0 is a generalization of the notion of rational equivalence of divisors. So for codimension R cycles, you look at rational functions on varieties of one higher dimension, so one smaller codimension. And then if you have a rational function there, it gives you a combination of codimension R cycles in X, and then those generate this subgroup of rationally equivalent to 0 cycles. You can also talk about algebraically equivalent to zeros, which means so that would, to say that two cycles are algebraically equivalent means you have one cycle here and you have one cycle here, and you put them in. You can make a family where one sort of deforms into the other, and so that family should be parameterized by some base variety that should be connected, and then and so if you have and then you view that family of cycles just means it's a big one cycle on the total space, and then you just take the fibers of that. Okay, so that's algebraically equivalent, and rationally equivalent you can think of as coming from algebraic equivalence when the base is P1, and then you look at the fibers above 0 and infinity. Okay, and then even weaker is just say homologically equivalent to 0, and that means that the class under that cycle class maps to 0 in the Tate homology. And this, a priori, this depends on L, because you have to choose for defining Tate homology. You have to choose your L. So that's why. So I put a subscript L there. And finally, you can talk about numerically equivalence to 0, which means that when you look at the intersection number with any cycle of complementary dimension, then that always gives 0. And okay, so it's not too hard to see that each of these is contained in the next. And so you get this, and then you can take, by definition, the cycle class map factors through. The kernel is by definition the Hom L, and so all these other things will be in the kernel too. So that means that the cycle class map you can also view it as a map that it factors through any of these, at least the first three quotients. Yeah, and this first quotient is a generalization. Yeah, it's called the codimension R Chow group, and when R equals 1, then it's just divisors modulo rational equivalence, so that then it's just pick, and then this one in R equal 1 is the narrow Savary group, and this one is, it turns out to be a narrow Savary group mod torsion. And so this one is just modding out by the full kernel, so that's also the image of this class group. Okay, so so now I'm ready to state these other sort of supplementary conjectures that are often viewed as part of the Tate conjecture. So the first one is E stands for equivalence of equivalence relations. So it says that the homological equivalence should be the same as numerical equivalence, and so in particular that will imply that this Hom L is actually that it's independent of L. Oh, because this one obviously is independent of L. Yeah, and this is known for codimension 1 cycles. And so the next one is that if you quotient up by this kernel and then you tensor with QL, then this is injective. If I didn't tensor with QL, then this would be a tautology because Hom L is the kernel. So what this is really saying is that to say this is injective means that if you take Z independent elements of this image of the class group, which is the same thing as this quotient group, if they're Z independent, then they remain QL independent in here. So the algebraic so these algebraic classes, if they're Z independent, then they stay independent over QL. And okay, this is sort of a side conjecture, but there's a much stronger conjecture, almost ridiculously strong, that says you don't even have to. That's the same thing is true even if you just quotient by rational equivalence. And this is maybe maybe it's surprising because usually in higher codimension there's a huge difference between cycles that are just homologically equivalent to 0 and and that are rationally equivalent to 0. So, but this is very special. So, but anyway, Bailen's conjecture is something very special happens when you're doing this over a finite field. Okay, so, all right, so one of these other supplementary conjectures, which maybe looks a little strange here, but let me just, says that if you take the Tate cohomology and you take the invariants, the Tate classes, then there's a map from that to V sub the co-invariance, which, okay, so this is the largest subspace that's invariant under the Tate that's invariant under the Galois group. This is the largest quotient on which the Galois group acts trivially. And so there's a natural map here induced by the identity because this is from the sub thing to the quotient thing, this subspace of V to this quotient space of V. And it's conjectured, and the conjecture is that this is an isomorphism. And this is really, you should view this as being a special, it's a partial semi-simple, there's a more general conjecture that this V is actually semi-simple as a representation of G. And this is a partial version of that. For example, if you do this for a finite field, then the G is just topologically generated by the Frobenius. And then this is a question about the eigenspaces in fact, it's a question about the one eigenspace, the fixed part. And it's saying that the one, it's saying that the one generalized eigenspace is the same as the one eigenspace. So in other words, it's saying that the multiplicity of the eigenvalue 1 is equal to the dimension of the Tate classes. So that's also part of the conjecture. Well, Tate calls it folklore. I guess a lot of people, in his 1994 survey on it, he credits all these people with explaining various aspects of this. But it's more or less formal that these two things. Formally that these two conjectures, the main Tate conjecture plus this Hom equals num, that those imply these other conjectures. And to do this, you use Poincare duality, the pairing with the complementary cycles, and the Hard-Lefschetz theorem, which gives you another isomorphism, and then from using that and just it's a formal constant. Formal constants means linear algebra pairing stuff, and so you can get all of these. Okay, so sometimes people view the combination of these two as being the Tate conjecture, that implies all these other nice statements. Okay, so I've explained one source of one reason one way that Tate came to the Tate conjecture, starting from the finiteness of Sha, and so I want to explain the other one that also Milne mentioned yesterday, which comes from the Birch-Swinner-Dyer conjecture. And so to do this, I have to say a little bit about zeta functions. So zeta functions you can define quite generally. So you can, for any finite type Z scheme, and you can define a zeta function by taking a product over closed points of 1 minus the size of the residue field to the minus S, and then minus 1. And you can check that if X is spec Z, then this gives you the Riemann zeta function. And if X is a variety over, another special case is where X is a variety over a finite field, and then this gives you the zeta function that you define there. Okay, and you can, by counting closed points, you can prove that this converges at least for complex numbers of real part greater than or equal to the dimension of X. And conjecturally, it should just like the Riemann zeta function, it should have a meromorphic continuation to the whole plane. Okay, so for this, we're going to look mainly at the case of a variety over a finite field, in fact, a nice variety. And in that case, then we have the Weil conjectures, which tell you more things about this zeta function. So I'll just quickly review that. So here you have in this case, you have the Frobenius, maybe I should say, this is the Q power Frobenius morphism. So this is the geometric map over FQ that raises coordinates to the Qth power. And it acts on cohomology on each, and then you can take the reverse characteristic polynomial of that. And that gives you some polynomial a priori has QL coefficients. But then the Weil conjectures will tell you, and these are I'm sure you all know these are not conjectures anymore. But okay, well, okay. Actually, I don't know. Does a conjecture cease to be a conjecture after it's proved? I'm not quite sure. Okay. Anyway, so yeah, these polynomials have integer coefficients and it's also independent of L, and the zeta function is a rational function that you can express, a rational function in q to the minus s that you can express in terms of these polynomials. It's an alternating product of these. And finally, this polynomial, if you look at its complex roots, then they all have this absolute value. So that means you can sort of separate out you can sort of see the different pieces of this, but just because even if you just know the rational function, you can separate the different parts because they have roots of different absolute values. And now from this, you can ask, well, if you ask about the order of the pole that this function has. By the way, this thing is going to have some poles that come from the denominator and zeros that come from the numerator. And the poles are going to have real parts 0, 1, 2, 3 up to d. And the zeros will have real parts along the real part equals 1/2, real part equals 3/2, real part on the half integers up to d minus half. And so so let's look at what happens to the order of the pole that comes at R. So this is all because of this Riemann hypothesis statement. All these poles are just coming from the P2R term, and so it's the same as looking at the order of vanishing of that polynomial at this. And so and if you can express it in terms of t equals q to the minus s, then you take the order of vanishing q to the minus r, and well, because this is a characteristic polynomial, a reverse characteristic polynomial, this order of vanishing is the same as the multiplicity of the eigenvalue. And if you put in the Tate twist, then this eigenvalue corresponds to eigenvalue 1 on this space. And so this order of this pole here is really measuring the multiplicity of this eigenvalue of 1. And so if you believe this partial semi-simplicity conjecture, that should be the same as the dimension of the eigenspace, not just this is the dimension of the generalized eigenspace for eigenvalue 1. But it should be the same as this. And then if you believe the Tate conjecture, then and the injective, you should be able to replace this space of Tate classes should be the same as the space coming from the cycles. And so you get that this, so if the Tate conjectures are true, then this order of the pole should be the same as the rank of the group of cycles modulo numerical equivalence. And so, and conversely too, the only way that this can be equal to this is if all these inequalities are equal. So the conclusion of this is what Tate realized and published in 1965, that for a variety, then if you know the Tate conjecture, meaning TR plus this equivalence for any one L, then it tells you that the rank of the group of cycles modulo numerical equivalence is this order of the pole. And and he also, I'm not going to talk about it now, just for to save time. But he also had a conjectured a generalization of this part B, not just for varieties over finite fields, but also for a variety over a finitely generated field. So it's again the Tate. Okay. So, all right. So let me leave that there. Okay. So so I'm not yet done explaining why you should now believe why you should believe the Tate conjecture. But let me just, the next ingredient is the BSD. So as I was saying, we want to look at what BSD says over a global function field and try to translate that into something about the total space of the family. So okay, so here's the So here's the conjecture. I guess you probably don't need to say much about this. So so it's made by Birchton and Dyer conjecture for elliptic curves over a number field, and Tate, well, I guess there's not much work you have to do to generalize the rank statement to this, but I guess what Tate also figured out what the full statement should be in terms of the leading term. So that's figuring out that is more work. But anyway, for now, let's just talk about the rank statement, that the rank is the order vanishing of this L function. And so as I was saying, to get to the Tate conjecture, Artin and Tate were looking at what this would say in the case where this J is the Jacobian of a generic fiber in a fibered surface like that. So, okay, and so the question is, given that setup, what does BSD say in terms of the total space of the family? So, for example, I mean, if you took it could be that J is an elliptic curve, and this could be an elliptic surface, and you want to say what does BSD for the elliptic curve over the global function field say about the surface over a finite field? Okay, so to do this, you have to work on both sides of this and re-express both sides in terms of x. And so, okay, so let's start with the left-hand side. For the left-hand side, the relationship is quite easy. You relate the rank of that group, and that turns out to be related to the rank of the narrow Survey group of x. So, which is the group of divisors modulo algebraic equivalence. And this just comes from, well, in the assumption, okay, maybe I should have said this. I'm making an extra assumption just to simplify, just for this talk. Let me assume that this fiber surface has irreducible fibers. I mean, in general, you could have fibers that have multiple components. Some bad fibers could have multiple, but let me assume that it's just every fiber is just irreducible. Maybe singular, but irreducible. Yeah. So in that case, you have a map from the Picard group of your total space to the Picard group of the special fiber, and the kernel of that map. I mean, if you have a line bundle on the total space that restricts to give 0 on the generic fiber, it means that it's actually it comes from a divisor that's supported on vertical fibers, so fibers that don't intersect the generic fiber, and those are the ones that come from pulling back a divisor on the base. And so you get this sequence. So you get this short exact sequence here that, the line bundles here, pull back here, and so on. And then if you look at, if you just compare the ranks of this, then this is just a Picard group of a curve, and because it's over a finite field, the pic 0 is a finite group. So pic 0 doesn't contribute anything, and so pic of the curve will be just 1, and then for the same reason, pic and narrow Survey have the same rank because the kernel is pic 0, which is a finite group. And here, so here, this is not, the eta is not over a finite field, it's over a global function field, but you can relate, that's one more, the rank here is one more than the rank of pic 0, and pic 0 is the same as the Jacobian. Okay, so you know the ranks of all these, and now you just say, okay, the middle one's the sum of the outer ones. So that's what gives you this. Okay, so so going back here, that translates this left-hand side into something about x. And now let's do the same thing for the right-hand side. So for the right-hand side, I want to claim that that the order of that pole is 2 more than the order of the L function. And this this is also not too hard. You just write out what, you just take the zeta function for x, which is a product over all the closed points of x, and you can partition those closed points according to which point of the base they lie over. And so if you do that, then this zeta function will be the infinite product of all the zeta functions of the fibers, because every closed point of x lies over some closed point of b. And then if you write out each of these using, each of these is just of these fibers, x sub b. Yeah, so x sub b just means you have a point here, and then you just have for each closed point here, you have the fiber. And then now this is over a finite field, and so you can take its zeta function, and its zeta function, you can express using the Weil conjectures, right, as this alternating product of polynomials evaluated at the residue field to the minus s. And then so this is an infinite product over this finite product, but if you interchange the order, you can group all the like, for example, you can group all the H1 terms from all the fibers and put them together, and that's the definition of that. I mean, that's going to be essentially the L function, and then the H zeros of these curves, those are easy. Those just give you a 1 minus QB to the minus S inverse for each thing, and so if you take the product of that over all B, then you just get the zeta function of B. And similarly, the H2 that gives you, H2 is also easy, and that gives you the same zeta function value at S minus 1. And so you can just see what the order of the pole is for this, because the order of the pole, I mean, each of these terms contributes. Zeros of the L function will give you poles, but also because we know what the zeta function for the curve looks like, it also has pole at. This has a pole at s equals 0 and s equals 1, so each of these will have a pole at s equals 1. So that adds 1. So each of these adds 1 more to the pole order. That's why you get this plus 2 here. Okay, so now we can put everything together. So in this so BSD is saying that the rank of JFK is the same as order of vanishing. So this is BSD. Well, it's BSD plus 2 with the plus 2 added on both sides. But yeah, so but then and by geometry, algebraic geometry, we re-express this in terms of X, the rank of narrow Savary, and using these other easy ingredients, well, easy like the Weil conjectures. No, just kidding. So using these other easy ingredients, you can re-express this in terms of the pole order of vanishing of the zeta function, and then as a multiplicity of an eigenvalue. And so this and then you see that what you end up with is this conjecture that the rank of the narrow Savary group is this multiplicity of this eigenvalue. And that's and this what is this multiplicity of this eigenvalue? Well, if you assume this I mean in this E1 is known, so this is the same as the dimension of the fixed space, the dimension of the space of the Tate class in here. So you should just start, even if you don't know the Tate conjecture, if you knew these other ingredients, you could just this, and this is what Tate realized, that the Burstner-Dyer conjecture is then equivalent to the Tate conjecture for X, and vice versa. I mean, so you can just from this diagram. So all right, good. So. Okay, and they also translated, I mean, this is just the rank statement of the BSD, but you can also translate the full BSD with the leading term part, and that'll also give you, and they also use that to get a conjectural formula for X that Milne wrote in his yesterday. So, I mean, proving this, even assuming finiteness of Sha, it took a long time, and it was mainly to get the power of P right, because you have to understand. Anyway, so a lot of difficult work was done by a lot of people who, Anyway, so but now as Milne mentioned yesterday, we have this theorem that in this context for a fibered surface, all these conjectures are equivalent to each other. So even if you know the Tate conjecture for 1L, then the Tate conjecture for 1L is then you automatically get it for all the other L's, and also it's equivalent to the Brauer group being finite. And to get the finiteness of the Brauer group, it's enough to prove the finiteness of the L primary part for any 1L. Or you could also do it the P primary part, where P is the characteristic. If you know any one of those L's, then you get the fineness for all the other L's, and you get the fineness of the whole group, in fact. And that's also equivalent to the same things for Tate-Schaff average group, and if you have this, that's also equivalent to the rank statement, the equality of ranks in the BSD. And if you have any of these, then you also get the full BSD with the leading term formula. So it's a really great situation, except that we don't know how to prove any of these things yet. So, Yeah. I mean, this is much stronger than what's known in the number field case. I mean, so in the number field case, we don't know, for example, if you know that Sha is finite, we don't know yet that that implies the full BSD. Or even the rank statement, yeah. Okay, and moreover, to prove the Tate conjecture for all, I mean, this is just for fibered surfaces, but actually if you, I mean, every nice surface can be represented as a fiber surface. You can just choose some rational map to some curve, even P1 if you want. But, so these are all equivalent to the Tate conjecture for surfaces. And also, it's known that Tate conjecture for T1 for surfaces implies T1 for all higher dimensional varieties as well. And also, so that's one reduction. So I mean, the stakes are pretty high for proving. If you prove the finiteness of Sha, then you'll get yeah. I mean, you don't get $1 million, but you get a lot of other things. Yeah. Also, I mean, you can also do a specialization argument. I mean, this T1 in general is about varieties over arbitrarily finitely generated fields, but you can actually reduce it to the case of the prime subfields. So either reduce to case of FP or to the case of Q. So yeah, and then so you just have to prove for surfaces over fine fields and surfaces over Q, and that's enough. All right, good. All right, so let's see. So let's see. I think I have time to say a little bit about another motivation that Tate had for there's a third motivation for the Tate conjectures, and this concerns a statement that Tate first conjectured and then proved for abelian varieties over fine fields. Okay, but the statements I mean, these days we know the theorem for arbitrary finitely generated fields. So let me state it in that form. So if you have a finitely generated field and you have an abelian variety over that field, you can form the Tate module and the ZL. This is a ZL module, and you can also form the QL module version of the Tate module. And these are like first homology. This is like first homology with ZL coefficients and first homology with QL coefficients. So these are very closely related to the cohomologies that we were talking about earlier, the étale cohomologies that we were talking about earlier. It's just more, maybe just a more concrete, more explicit way to describe these in the case of an abelian variety. Okay, so and then whenever you have a homomorphism between two abelian varieties, that induces a map between these vector spaces. And if the morphism is defined over the ground field K, then that morphism between the Tate modules will be invariant under the Gallo group, and so so the conjecture was then that this map should be that if you conversely if you have a Gallo invariant linear map between the Tate modules, it should come from actual algebraic homomorphisms. Yeah. Okay. So I mean, as you can see, it looks quite similar to the Tate conjecture, except instead of cycles, we're talking about homomorphisms. But I mean, there's a close relationship between, say, homomorphisms from A to the dual of B and divisors on A cross B. So yeah, and so because of this, you can prove, using things like this, you can prove that this statement is equivalent to proving the Tate conjecture for divisors on all abelian varieties. So if you know, yeah. And the other thing is, the reason that this is a nice statement to have is that if you know this statement, then you can relate the Tate conjecture for divisors on X cross Y to the Tate conjecture for X and Y. I mean, a priori, they're not quite equivalent, because if you think about what they're saying in terms of, this is saying something about the H2, and the Kunith formula says that H2 of this involves more than just H2 of X and H2 of Y. There's also the H1 tensor H1 term, and it's the H1 tensor H1 term that's the statement for that is essentially this, and so But if you prove this, then you don't have to write that on the right-hand side here. So that's why this. So this statement is also, you can think of as being something that it's sort of it's also compatibility with products. It says that that Tate's conjecture is compatible with products. So okay, so yeah, and if you so Tate can prove this over finite fields, and then it was later proved for finitely generated fields of characteristic P, and then finitely generated fields of characteristic 0 by Zarhin and Feltings. But even just the statement for finite fields has very nice implications for the category of abelian varieties up to isogeny. So this is the category where you take the objects or abelian varieties over FQ, but you take the Hom groups and you tensor them all with Q, so that isogenies become invertible then. Yeah. So using this and using the Honda's construction of abelian varieties with given characteristic polynomials by taking CM abelian varieties constructed analytically over C and descending them to the number fields and then reducing them mod P to get abelian varieties over finite fields. If you combine that construction with this theorem, then you get a very explicit description of what this category looks like. And so that was a very nice consequence of this as well. And okay, and this, I mean, the number field version of this, I guess, this also has pretty nice consequences as well. So, I mean, yeah. So okay. Anyway, so let me try to say a little bit about about the proof of this conjecture. So actually, I'm going to cheat a little bit. I'm going to simplify a little bit using Zarhin's trick, just because what Tate actually did was harder. But after you know Zarhin's trick, then you can simplify this. So okay, so the first step. So by the Hom theorem, I just mean this theorem, and I'm just talking about the case over a finite field. Yeah, this is what Tate did, and yeah, Tate wrote that he was very happy to prove this. But so yeah, I think we're all happy that he proved this. So okay, anyway, so yeah, so the first step is this finiteness statement that if you look at all abelian varieties over a finite field of a fixed dimension and a fixed finite field, then there are only finitely many of them. And what makes this hard is that there's no principal polarization here. If you had principal, if you had principal polarization here, then it would just follow from the fact that you have a moduli space. It's a finite type, and then you'd be more or less looking just counting points of that variety over a finite field, and so you'd have finitely many. I mean, there's a little bit issue with twists, but there are only finitely many twists for each one too. So, but okay, so this is where Zarhin's trick comes in, because if you want to classify all abelian varieties, you can use the trick that each abelian variety is a direct factor of a principally polarized one, and what Zarhin actually proved is that if you take any abelian variety, then A to the fourth cross its dual to the fourth has a principal polarization, and then A is a direct factor of that. And that multiplies the dimension by 8, but that's okay, because it's still fixed. If G is fixed, then 8G is fixed. So yeah, so you get all the abelian varieties as direct factors of these principally polarized ones, and as I said, there are only finitely many principally polarized ones. And then just there's a statement of geometry of abelian varieties. You can prove just by studying their endomorphism rings and so on. You can prove that each of these, any given abelian variety has only finitely many direct factors up to isomorphism. So yeah. So if you put that all together, you get this fineness statement. Okay. So then the key part of the argument is this next part. So okay. So first of all. So in proving the Homs theorem, that the Homs relate to the Homs between the Tate modules, you can, because the Homs you can view as like the upper right corner of a 2x2 sort of matrix group for the endomorphisms of this product. You can reduce the statement for Homs to the statement for the endomorphisms of A cross B. And so by doing that, you can, instead of talking about Homs, you can prove it suffices to prove the theorem for endomorphisms of this higher dimensional variety. And so from now on, we're just going to be talking about endomorphisms of a fixed abelian variety, which I'll now rename as A. And then I'll let T be the Tate mod, T and V be the ZL and QL Tate modules, and now E will be the endomorphisms tensored with QL. And so what we're trying to prove is that E maps to the map from E to the endomorphism ring of V maps is surjective onto the Galois invariance of end of VG. And the key step is to prove that if you have inside here, if you have a G-stable subspace, then it's actually the image of something that comes from endomorphisms up to tensor with QL. And, well, I mean, the argument for this is, well, I mean, so to do this, you have to somehow, the hard part is you have to somehow cook up some actual endomorphisms just from knowing some linear map that's Galois stable. And what the linear map, and here we, instead of a linear map, we're talking about a subspace. But what this subspace gives you is it gives you a chain of G-stable submodules of the Tate module of T. Namely, you can, well, first of all, you can take this, you can intersect it with this subspace to get a direct factor of T that's Galois stable, this T prime. But I mean, this is T prime is just a lower, it's a ZL module of lower rank inside T. It's a sublattice, saturated sublattice of lower rank. And then from that one, you can build submodules of sublattices of finite index in T by taking L to the n T, which yeah, you just scale it down by L to the n, and then take that together with the part that's in the direction of T prime, and then that together will gives you, yeah, and then as n increases, this gives you a sequence of sublattices of all the same rank as T, but the intersection of all of them will be just T prime, will be this lower rank thing, and then because these are all finite index, then just they correspond to isogenies, because this just amounts to, like, you know, I mean, if this module is contained here, that just means that this A is a quotient of Bn by some Galois stable finite subgroup, and so you get an isogeny, and so now you have this whole chain of isogenies going back. You have A, and then you have A. I mean, corresponding to these submodules indexed by n, you have this sequence of isogenies, of L power isogenies going back. And now you use the first lemma that says that there are only finitely many isomorphism types. So in this list of abelian varieties, they're all of the same dimension. They're all isogenous to A. So there's one of these will appear infinitely often. Say maybe this one and this one and this one. And this one. Maybe they're all isomorphic to some particular B. And so you have all of these isomorphisms here. And so you can view all these, each of these isomorphisms gives you a different homomorphism from B to A. And so you have this chain of homomorphisms, and each one maps the Tate module of B onto a different submodule, a different sublattice of T. And so, yeah, so so you have all those homomorphisms, but then they'll have a limit. The limit won't be a homomorphism anymore. But in this, when you tensor with ZL, then you get a compact group, and you can take a limit of some convergent subsequence, and you'll get some phi it's not really a homomorphism, but it's a homomorphism tensored with ZL. And this one maps the Tate module onto the intersection of all these. Because when you take the limit, you'll get this descending sequence. You'll get this T prime, and so that gives you a homomorphism from B to A that maps the VL Tate module onto this Galois subspace. That's not quite what we wanted, because this is supposed to be an endomorphism, not a homomorphism from some other abelian variety. But that's easy to fix, because B is isogenous to A. You just compose with any old isogeny from A to B, and that'll give you this thing, this U. Okay, so I don't have much time. Maybe I won't do the last part of this. The last part you want to prove that the endomorphisms surject onto this V, and you apply you have this Galois-stable homomorphism. You apply the previous lemma to the graph of the Galois-stable endomorphism, and you use the double Covington theorem, and you get this theorem. Okay, so that's the end of the proof of the Hom theorem. So the last thing I want to talk about is, pretty much everything I've been talking about has been ancient history, but let me talk about something which is not quite as ancient. So this is an algorithmic aspect of the Tate conjecture. So you can ask, is the Tate conjecture actually good for computing anything? I mean, it's not clear because, yeah, I mean, so what we prove is that you can actually, if you believe the Tate conjecture, you can compute the narrow Sévère group of X over